Hello everyone, my name is Qingrong Chen. Today I will give a presentation on our work, understanding and discovering software configuration dependencies in cloud and data center systems. Configuration management in cloud systems could be challenging. First, cloud systems could have a large number of configuration parameters. For example, there are hundreds of parameters in Hadoop and OpenStack. Second, many configuration parameters are interdependent, and failures to recognize those dependencies could lead to real-world issues. What's more, the dependencies could also cause multiple interacting components, which makes management more challenging. In the next following slide, I will show you several examples about configuration dependencies. The first example is an intra-component configuration dependency. Here, we have three parameters from MapReduce. The dependency relation here is P1 should be less than P2 and P1 should be less than P3. If the dependency relation here is violated, then failure nodes in MapReduce could not recover due to retry failures, which means the retrying logic in MapReduce will fail. MapReduce does not check this dependency. But after this issue was being reported by several users, this dependency became documented after version 2.0.2. The second example is an inter-component configuration dependency. Here we have four parameters from HBase and HDFS. The dependency relation here is P1 should not be less than the sum of P2, P3, and P4. If the dependency relation is violated here, then the least recovery procedure will fall in infinite loops, which stacks the whole program. This dependency was already labeled as a major bug in HBase. However, there still exists no checking codes for this specific dependency. After viewing the previous examples, we can see configuration dependencies can be quite complex, such as crossing multiple components, and cause real-world issues. In this work, we managed to tackle this problem from three aspects. First, we try to understand and formally define configuration dependencies. We care about both intra and inter-component dependencies. Second, we try to characterize the common practices in configuration dependency management. We care about how configuration dependencies are checked and how configuration dependency violations are handled, and how configuration dependency violations are logged. Finally, we deliver a tool, cDep, which can do automated configuration dependency analysis. In the following slides, I will describe each contribution by sequence. First, let's take a look about understanding configuration dependency. The challenge in understanding configuration dependency is there exist no formal specifications of the configuration dependencies. And before we do this study, we don't really know what configuration dependency means exactly. Also, enumerating all possible dependencies could lead to combinatorial explosion. And in our study software stacks, OpenStack and Hadoop, there are hundreds of parameters. However, although there exist no formal specifications of configuration dependencies, we find that dependency information could actually be collected from some documentations, like configuration parameter descriptions and user tutorials. Here is one example from configuration parameter description, where we can see the parameter file bytes per checksum. In its description, we can explicitly see such dependency relation. It should not be larger than another parameter, file stream buffer size. We also have one example case from user tutorial where one parameter will activate the AES encryption and the other parameter will decide the key length used for this AES encryption. Based on this insight, we present our methodology as follows. We will try to analyze both structured and unstructured text data. Structured text data refers to configuration parameter description, and unstructured text data refers to user tutorials. We apply several heuristics for mining potential cases from those text data. For structured data, if a parameter is described in the description of another parameter, we will label them as potentially related. For unstructured data, if two parameters are described in the same paragraph, we will also label them as potentially dependent. After we get all those potential cases, we verify them by doing source code inspections. And this whole process takes 12 person-months efforts. So here is the final dataset we have after we finish the manual inspections. Our dataset contains data from two multiple component software ecosystems. There are 8 components from Hadoop-based data analytics stack and 8 components from OpenStack. We find 424 intra-component dependencies in total. 219 dependencies out of them are from Hadoop, and 205 out of them are from OpenStack. We find 97 inter-component dependencies in total. 94 out of them are from Hadoop, and 3 out of them are from OpenStack. After we build this dataset, we try to categorize each dependency case into different types. There are big categories we consider when we do the categorization. The first big category is what we call functional dependency. And this means a configuration value is influenced by other configuration values. Based on what that influence is, we have 4 specific configuration dependency here, which are control dependency, default value dependency, override dependency, value relationship dependency. Another big category we consider is behavior dependency. And that means a set of parameters will influence together the system behavior. Due to time limits, in the presentation, I will only describe 3 dependencies: control dependency, value relationship dependency, and behavior dependency. For other dependencies, please refer to the papers for more detailed descriptions. First, let's take a look at the control dependency. Control dependency means whether a parameter value can be used or not depends on the values of other parameters. And this could add a complexity for users to use this system. Let's take a look at the example here. Here we have 2 parameters. The first parameter fs.client.resolve.topology.enabled will determine whether we want to enable this topology feature for the file system. And only when this feature is enabled, we will use the value of the second parameter, which is net.topology.node.switch.mapping.implement. And this means if the user wants to use the value of the second parameter, the user needs to remember to set the first parameter to be true first. Otherwise, whatever value user assigns to the second value won't matter here. The second dependency we want to introduce is value relationship dependency. And this means a parameter value is constrained by other parameter values. And failure to recognize those dependencies could terminate the systems. So here we show you one example from a Luxio, where we have 2 parameters. One parameter denotes the minimum worker stress for Luxio, and another parameter denotes the maximum worker stress for Luxio. And it's very obvious that the minimum value should not really be larger than the maximum value, right? So if the system ever detects such violation, it will direct terminate the system without really going forward. The third dependency type I will describe is behavior dependency. And this means a set of parameters are used in the same operation, such as library and system calls, to influence system behaviors. And failure to recognize this dependency could fail those library or system calls. Here, I show you one example where we have 2 parameters. One parameter will denote the host address for FTP service, and another parameter will denote the port number for the FTP service. And we know different ports could be available for different hosts, right? So if a user set a specific port number which is actually not available for that host, then the connection library call here will fail. So here are all the main findings after we finish all the characterizations. The first finding is that control dependency is most common in our dataset. More than 50% of those dependencies are control dependency. The second finding is around 31% dependencies are value relationship dependency. As we discussed before, violations of such dependency could lead to reliability and performance issues. So it's pretty critical that we should have good handling and checkings of those violations. We'll discuss more about this point in the following slide. The third finding we have is OpenStack has fewer inter-component dependencies than Hadoop. The main reason is in OpenStack, each component uses RESTful APIs to communicate, and each component only does independent service. However, in Hadoop, different components could share many libraries. After we understand what configuration dependency is, we look into the current practices of dependency management. There are several questions we specifically care about. The first question is, how well are configuration dependencies checked in current software systems? The second question is, if the configuration dependencies are checked and the system detects some violations of those dependencies, how well are those dependency violations handled? And the third question is, if the system detects dependency violations, how much feedback the users can get? And here is the observations of the first question. We find most configuration dependencies will have checking logic. Specifically, we have 89% in Hadoop and 71% in OpenStack have a checking logic. However, this shows there still exists a certain percentage of dependencies which are unchecked. So this shows we require more systematic checking practices for configuration dependencies. Regarding the second question, how are dependency violations handled? Commonly, violations are checked and lead to early terminations in the system. Specifically, 33% cases in Hadoop and 40% cases in OpenStack will directly terminate the system when detecting such violations. Also, we identify a significant percentage of violations could crash the system at runtime. Specifically, around 6% in Hadoop and 33% cases in OpenStack will terminate the system in runtime after detecting such violations. What's more, we also find there are also some cases which can correct those violations by overriding invalid values set by users. Specifically, 45% cases in Hadoop and 22% cases in OpenStack will overwrite those invalid values set by users. So how much feedback user can get after detecting such violations? We find a significant percentage of violations are actually not logged at all. Specifically, 36% cases in Hadoop and 15% cases in OpenStack does not have any log messages for violations of configuration dependencies. We also find many violations are logged only with partial information. Specifically, 38% cases in Hadoop and 42% cases in OpenStack only provide partial information for users. Here we show you one example about this partial information. From this log message, we can see the user could not really tell what the exact configuration dependency relation here is and why that relation is violated here. We also find less than 50% of violations actually are logged with complete messages. Specifically, 25% cases in Hadoop and 42% cases in OpenStack will log with complete information. Here we show you one example. And you can see from this specific example, users can easily tell what the involved configuration parameters are and why this dependency relation is violated here. After we finish the study part, gain understanding of what configuration dependency is and how configuration dependencies are managed in current systems, we leverage those findings into building a tool called cDep, which can do automated configuration dependency analysis. In a very high level, cDep will take Java bytecodes as input and output intra and inter-component dependency cases. In the design level, cDep uses static program analysis. cDep will analyze how configuration parameters are used throughout the whole system, and cDep will also analyze how configuration parameters interact with each other. There could be several potential use cases for cDep. First, we could try to use cDep to enhance configuration dependency documentations, because after we find all those cases, we can basically create a web page for document all that information. Second, cDep could be used to improve software configuration design. After we know all those dependency cases, a natural question is, Are those dependency cases all necessary, or can we come up with better designs to eliminate some unnecessary configuration dependencies? Finally, cDep can also be used to do checking and violation handlings of those dependency types. So here is a concrete workflow of cDep. First, cDep will try to locate the configuration APIs, which is config get int in this specific example. And this function will be used to read the parameter values from the configuration parameter file into this program. In this example, it will be used to read the parameter value of dfs.replication and dfs.replication.mass. And then we will tend the variables which stores the values of those parameter values. Next, we will do both intra and inter-procedure tend trackings to track how those tented variables are used throughout the program. In this example, we can see this replication variable is passed into the parameter of this function verify replication. And finally, we will try to locate the statements where using the code patterns we summarized from the study part. Here we can see this code is trying to compare the values of two tented variables, replication and max replication. In that case, we will directly output them as value relationship dependency type. So here is the final result for cDep. cDep is evaluated over 8 applications from the Hadoop stack, since currently cDep only supports Java bytecodes as input. cDep is able to find 448 more dependency cases, which actually shows dependency is not really real in current software systems. cDep has around 6% false positive rate. The main reason is due to over-tenting. cDep does not really implement the feature path sensitivity. cDep also fails to identify 38 dependencies from the dataset. One reason is because some systems use some ad hoc ways to overwrite the configuration values instead of using standard configuration APIs. Second, 14 dependency cases does not really have common source code patterns. Finally, cDep does not really analyze any external library calls, which is defined outside of this project. So here is a conclusion for our project. In this project, we try to understand and formally define different types of configuration dependencies. We also conduct an empirical study on practices of configuration dependency management. Finally, we deliver a tool to do automated configuration dependency analysis. All the codes and dataset in this project could be accessed through this website. Thanks for your listening. That's all for my presentation today.